Welcome to day 2 of equilibrium. We learned yesterday that if a reaction's at equilibrium, the forward rate and the reverse rate are equal to one another. All right. The elementary way we said that is it means the reaction has stopped. It's not doing anything. I lost my goggles. So, with that said, I've got some chemicals here. 3 of them. And do you think that the way they're set up right now, would I consider this environment to be at equilibrium? No, I wouldn't. Because while nothing's happening, equilibrium is when a reaction has had its rates equalize and stop, and nothing's happening. You know what word I would use to describe this situation? Initial. That's a big word for us today. These are initial molarities. I can figure out what their molarities are. They're not at equilibrium yet. Yesterday, I introduced you to K, which was, to find K, the equilibrium constant, it was products over reactants raised to the power of their coefficients. That math is really important. The K is super important, but those values that we did yesterday, they were all at equilibrium. The reaction was already not moving. Again, these are initial. If I were to take the molarities of these items, I couldn't put those into a K expression. Because the only stuff you can put in there is equilibrium values, not initial values. Now, if I force the reaction to go, though, now before I force it to go, since it's Halloween, I thought we could maybe murder the reaction a little bit. There we go. It's kind of murderous. Can you see it there? It's red. But I know that some of y'all are scared of murder, so then we turn it into Christmas instead, because nobody's scared of Christmas. Maybe you're scared of Christmas. Nice and pretty, yeah? Anyway, that doesn't have anything to do with what we're doing. So, initial, let's force the reaction. Kind of fun, but then it gets more fun because while it's running, it starts to get a little bit bigger. Hey, is it at equilibrium right now? No. Is it at equilibrium right now? No. What about now? Because it's not at equilibrium until it looks like nothing's happening, right? Forward and reverse rates the same. So, sorry, you people at home, I'm going to take you away, but it's not going to do anything else. But y'all are welcome to keep an eye on it. Of course, eventually it will reach equilibrium. But our big distinction today is going to be the difference. Make sure you have your slides at home. Is going to be the difference between when they give us equilibrium and when they give us initial. Really, if I were to say the thing that might cause you the most trouble on the upcoming exam, it would be realizing that if they give you equilibrium values, you do what we did yesterday. You do this, right? Those black numbers from yesterday's work, those were equilibrium, so you stuck them straight into a K expression. That's one of the things that the test will make you do. A different thing it can make you do is instead of giving you that equilibrium stuff, it could give you initial stuff, which is what I had before things got sudsy. And you have to do a rice table. But there's also a third option. It could give you data while the reaction is moving. It's already started and it hasn't stopped, in which case you have to find Q. So, the question on the exam is, can you figure out which of those 3 random problems you're looking at because you solve all of them a different way? So I showed you the equilibriums yesterday, which is the easiest. Let's do initial today, which requires rice. You can see that it lets you know up there that you'll have to use a rice table. It's an acronym. If you're given initial data instead of equilibrium. I wish we were talking about yummy rice. Who likes fried rice? Fried rice fans in here? Is it better or worse with egg in it? No. No, sir. If you come to my hibachi, we are not putting egg in the fried rice. Anyway, you're going to want the RICE meanings in front of you because while we go through this initially, it's going to feel really weird because you've never done it before. So you're going to want to reference how I know what to put where. Let's dive in. All right. So we've got our first problem here. We're going to do 3 problems today. If you take a look at the way the problem reads, it says that a 1 liter container holds some amounts of different things. It's just sitting there holding amounts of things. A reaction hasn't happened. It's at the beginning. Context clues are a big part of this. But then later in the question, you can see that it mentions after equilibrium, then it gives you other data. All right, so that reiterates the idea that the other data was before anything happens. Now, in order for us to use initial data, we must do a rice statement. You write what I write. If you glance back to the previous slide, you will see that R stands for reaction. You just rewrite the reactions. Let's write it. 2H2 is reacting with carbon monoxide at equilibrium with, watch your arrow there, CH3OH. All right. Hey, look at the states of matter. Are those states of matter okay for this? Now, what are you asking, Cummings? What does that even mean? Well, yesterday, we know that if you're doing K or KC, the states must be aqueous or gaseous. You're doing KP, it has to be gaseous. But all of these are gaseous, which means no matter which one it is, it's KC if you look at the question. Gaseous is good. So we don't have to ignore anything. Let's go talk to someone, though. Let's go over to cluster 2 and talk to seat 5. Hey, 2-5, what does I stand for? You don't have your notes. It would be in your notes. Initial concentration. Now, concentration is the same as molarity, of course. And you'll notice that this doesn't give us that. What does it give us? Moles. Y'all, moles cannot go anywhere anywhere. Moles is never okay. But look at the liters. What's the liter value? Yeah, to turn it into molarity, to turn it into the concentration you need, it's moles divided by liters. But the liters in this question is 1, so you'd have been all right. Any number divided by 1 is itself, right? So we'll turn it into molarity, but when you do, here's the values that you should get for each. You should get 1.06 there. The carbon monoxide is 1.57. You see those values in the question, yes? There's the initial concentrations. Hey, why is there not one for the product? Why does it make sense that the product initially is 0? Because you haven't done anything yet, right? It's initial. I'm standing in front of the stuff and I haven't mixed it yet. So of course there's no product. Nothing has happened. Let's go over to cluster 2 and talk to seat 4. Hey, 2-4, what does C stand for? Change. Now this row is a little weird for starters, but here's how you're going to do the change. First off, though, remember our equilibrium graphs from yesterday? what did the reactants always generally do? Go up or down? The reactants decrease while the products increase. Watch how the change is. The change for reactants will always be negative coefficient X. Reactant is negative because it's decreasing coefficient X. But the products will be positive coefficient X because the products are increasing. Positive coefficient X. Of course, there's some ones there. You'll get used to that. Are we okay? Now, if you look at E, first off, E, this is the magical row here. This is the one we care about. Because the problem that I have is I don't know the equilibrium values the way that I did yesterday. It just gave me those, so I went straight to K. Here, it gave me the initial values, which is the whole point of the rice table. I need to turn these initial values into equilibrium values, and then I could plug it into K and do what we did yesterday. In order to start getting this data, if you look at the opening slide, it says that the equilibrium row is I plus C. You're going to join the previous two rows together. 1.06 minus 2x, 1.57 minus x, and then 0 plus x is just x. Now, this is a fun moment for you. This is a more exciting moment than you even realize. Between now and Christmas, you're going to do so many rice tables for me if you count all of your Canvas work and all the lectures waiting for you. That this is your first one. So cute. All right. Remember this moment. The formatting to get to this point is always the same. I believe that you'll be really good at rice tables by the end of next week because you're going to do so many of them. The thing that makes this get tricky is what you do next, because it can always be something different. Here's what has to happen. The question has to give you a sprinkle of something else. This is not enough data to do anything else with now. All right, it'll give you enough data to fill out your rice table, but then there's always something else, and it could be different things that they'll let you know for you to drive forward. Let's look at what that extra thing is here. It says, at equilibrium. At equilibrium, it's giving me data from the E row. At equilibrium, the product is 0.2 moles. Now remember, moles is no good. You can never put moles into a rice table, but it's in the same container. So 1, all right, moles divided by liters. It is the molarity of 0.2. Here's what it says. It says that at equilibrium, the CH3OH is 0.2. It's flat out giving you this value to be a concentration after you do the division to its molarity of 0.2. Do you see how incredibly helpful that is? We now know the identity of X. And if you apply that identity to the other X's, you get all the E data, and then you can go back to yesterday. So let's do that. So for the hydrogen, it'll be 1.06 minus 2 times X, which is 0.2. For the carbon monoxide, it'll be 1.57 minus X, which is 0.2. And you can get a calculator out if you don't want to just trust me, but whatever, it's pretty simple math here. But now we can simplify, all right? Which means I can figure out that the concentration of the H2 is going to be whatever that is at equilibrium. What's up? I'm not subtracting. Where do you say? Oh, here. No, here it's multiplying. This minus X. This minus X. This one's multiplying. But there's still a minus on both. When I run that equilibrium for H2, I get a value of 0.66. 0.66. All right. When I run it for the carbon monoxide at equilibrium, the difference there is 1.37. And of course, it just gave us this because it was already X. So then the CH3OH at equilibrium is 0.2. Who's got questions or concerns about how we got here? Now, I want to point out that the question, if you look back at the screen, it wants those two numbers. The question asks for three things. It says, what is the equilibrium concentration of him? 0.66. What is the equilibrium concentration of him? 1.37. So if you're doing an FRQ, make sure you indicate that those are two of the three answers. But what else does it want? It wants K. So now we're back to yesterday. What type of equation do I say you should always start with when doing a rate, an equilibrium constant? Oh, the other two classes got this. Starts with a U. Unsubstituted, right? Remember yesterday? Unsubstituted. Here's what it looks like. Kc equals products over reactants raised to the power of their coefficients. So that'll be CH3OH is my product over H2 raised to his coefficient alongside Ca. Now remember, y'all, those red numbers up there could not go into this equation because they were not equilibrium numbers, they were initial. But the blue numbers are equilibrium because the Rice table is awesome. And now you can substitute. So we're going to go Kc equals the values. The C3, this will be 0.2 over the H2 will be 0.66. And then the CO will be 1.37. We are close now. Get an answer. Get that calculator up. Watch out for order of operations on the bottom there. Anybody brave want to shout out a KC? Yeah, I get 0.3. So your sig fig should go off your initial values, of course. What are the units of K? Nothing. Yay. We like it when there's no units. But the conclusion of K is really, really important, right? What's the conclusion based on that value of K? Remember, the whole point, if you're like, what the heck are we doing? The biggest point of this equilibrium stuff is when the reaction stops, when it stops being sudsy. Was there more reactant or product? What's the answer for this other thing? More reactant, is it favored in forward or reverse? Reverse. If K is less than 1, it's favored in reverse. Reactants. More reactants. Yeah? Now, if I see some of you still getting wrong answers, it's because of order of operations. Do the green again, but protect the bottom in parentheses right there, and it will fix your math. Let's do another one. Now, as I said, we're doing 3 of these. And they get worse with each one. I'm just showing you 3 different types of rice table problems, and it's scaffolded. Every one is worse than the one before it, so sorry. Hey, look at the new question. Remember, one of the big challenges that you're going to have is figuring out, do I use a rice table? Do I not need one? Do I do Le Chatelier? That's Tuesday. Look at the context clues there. This one's really nice, actually. What word tells you right away that you better go all rice table? Initially. See the word initially in it? The word initially is there, which definitely means the numbers it's giving you are initial, which definitely means we're going to rice table this dude. Let's get it going. R stands for reaction. Write it down. 2 nitrogen monoxides react with bromine to go to equilibrium with 2 Nobers. All right. Let's draw some cards. Let's go over to cluster 1, seat 5. Hey, 1-5, are we happy or sad about the states of matter in regard to them working? We're happy. They're all gaseous again. This one's actually Kp. If you look down at the question, it wants us to find Kp, which can only use gases, but they're all gaseous, so we don't have to ignore any data. All right? All right? Let's draw another card. Let's go over to cluster 4 and talk to seat 2. Hey, 4-2, what should I put right there? All right. So it stands for initial concentration or pressure, because these are pressures. Pressures are good. You don't even have to worry about this madness if it's a pressure. But see if you can find it. What's the number for the NO? That's correct. Pulled it straight out of the problem. The bromine initial pressure is sitting at 0.329. What's the initial pressure of the product? 0. We're initial. There's no product yet. All right, let's go somewhere else. Let's go over to cluster 6 and talk to seat 2. Aspen. What should I put right there?
Negative 2x.
Exactly right. You can pass the bird. Reactants are always negative coefficient X. Another reactant, negative coefficient X. But products are positive coefficient X. Are you sure, Serenity? Yeah. We doing all right? And then we have our best friend, the E row. I'm your hero. That's the E row. The E row is a combination of I and C. It's the E row that will get us the data that can go with K, not the initial stuff. So here we go. This will be 0.526 minus 2x. This will be 0.329 minus x. And then this one will just be 2x. Let me know if you are not okay. So that's just standard rice table stuff. What about the sprinkle? What's the sprinkle here? Now, I told you this one's a little bit more annoying than the last one, but just a little bit. It's just one extra teeny step. Let me show you why. After equilibrium, right? At equilibrium, I see that wording, and I know, I want my ruler. I see that wording, and I know right away that now, after equilibrium, it's going to give me something about the E row, which is a magical moment for me. And look what it says. It says that the bromine pressure, parentheses for pressure, the bromine pressure is 0.203. Now, this feels like the sprinkle last time, but here's why it's different. Last time, the species that it gave me the extra info on was just X. It handed me X. Remember? It was totally lined up for it. But look what happens this time. It's giving me bromine. Do you see how bromine's equilibrium expression is a bit more complicated? It is saying that this expression that represents bromine needs to equal that. It's easy to do. We'll just say, oh, okay, well then, we'll do it down here. No, I won't. Then 0.329 minus X needs to equal, because it says at equilibrium, bromine is 0.203. So whatever, it's 7th grade math. Find X now to apply elsewhere. And you'll see that X, give you a split second there. You should get 0.126. Are we all right? Subtract 0.329 from both sides. It'll become positive because it's negative. We good? Now it's like the last one. Now I know X, and we can just apply it to the other spots and find everything. So over here, it'll be 0.526 minus 2 times 0.126. Over here, it'll just be 2 times 0.126. And if you run the red, you'll get the other equilibrium datas. I get 0.274 when I solve that. And I get 0.252 when I solve that. Of course, these are all atmospheres. If you look at the problem. How are we doing? How's our brain working? See if you can finish it. It wants K. We've got the equilibrium stuff now. It's over there in brown. All you've got to do is go unsubstituted, substitute it, find it like yesterday. Take a minute, find KP.
Just because it's B doesn't change the equation.
The K equals products over reactants never changes. All the P means is that these will be in parentheses instead of brackets. I'm going to start doing some work up here. If you feel stuck, you can look at mine. If you don't want to, don't. Oh, wait, I did something weird. The number. Oh. I made a mistake. I rewrote the reactant in the product spot. Sorry, people at home. Yeah, remember this value that gave me the 0.252 was describing the product, which was Nober, and see if you can draw your conclusion about which direction it's favored based on the final KP value that I'm about to write down. If you did all that correctly, I get a KP of 4.17. If you got a number other than 4.17, run the purple again. Protect the bottom in extra parentheses. It'll help you out. Let's draw a card for that conclusion question, though. Let's go over to cluster 6, seat 2. Hey, Aspen, which direction is it favored based on the orange?
Forward.
Do y'all agree with forward?
Yes.
Yes. If it's greater than 1, you can pass the bird. Then it's favored towards the box. What do y'all think of this so far? It's bad? Okay. It's so bad. All right. The last one's bad. I apologize ahead of time. The last one's the bummer one, but we got to be good at it. So let's do one more, and it will be the worst part of our day. Whoops. Now, before we do our final problem, I want to point out this slide that you skipped. The way that I'm going to solve this final problem is going to be connected to the chemistry references folder on Canvas. You have access to the stuff I'm about to use. If you click on pathways, it'll give you ways to make your calculators do what I'm about to show you to do. That's fine. My preference, though, is to click online solver, which will take you to this 0 equals box that you'll see me model in a moment. So keep in mind that you've got those instructions there. Let's finish up. All right, if you look at this new problem, the thing I see right away is that it gives me K. We have not had a problem in this unit give us K yet. The spot that I see K given is it says the equilibrium constant for blah blah, the K is 33.3. If they give you K, it's a bad news, bad problem for you. Not in terms of being really hard, it's just a lot of work. So let's see if we can knock this out in 11 minutes, which is what I have. Not only does it give me that data, but it says, it describes that the reactant in that reaction is being placed in something. It's walking you through the start of the reaction. It says, We're placed this much in this. Context clues for initial. Initial data is a rice table. Here we go. I'm going to draw less cards this time, so it is your job to interrupt me if I do something you disagree with. I made a mistake last time and no one said anything. I hate it when that happens. All right, I like it a lot when y'all yell at me and see it right away. So focus, stop me if you have a question or anything. R is reaction. It looks like it's phosphorus pentachloride decomposing at equilibrium with phosphorus trichloride alongside chlorine gas. I noticed that the states of matter are all gaseous, and even though it's asking for Kc, that would still work for Kp, but this is a Kc problem. Or it gives us Kc, so I know it's concentrations. Initial concentration. Now, there's only one reactant, but look at the numbers this time. It says moles again, so we're right back here. We're like, moles cannot go into any part of a rice table ever. It's got to be molarity. Moles divided by liters. What's true about the liters this time? It's a number. It's the number 2. So it gives me point. Bless you.
Thank you.
I'm so sorry, y'all, that she did that to you. Redo the video now. It gives you 0.4 moles and 2 liters. 0.4 divided by 2 will give you a molarity of. And if you search the question, you'll verify there are no initial quantities of products given. C is change. Reactants always negative coefficient X. Products always positive coefficient X. But there's no coefficients. The important row, equilibrium. I plus C equals E. Join those rows together. Are there any questions? As I already mentioned, the sprinkle this time is K, which usually means quadratic things. The problem with K being the sprinkle is there is no way to use that to find the X's early like we did in the previous 2 problems. I have to go straight to a K expression. So do this with me. Let's go unsubstituted first, which is going to be Kc equals the products of PCl3 and chlorine over the reactant of phosphorus pentachloride. No exponents because there's no coefficients. Substitute. I know some things. I know Kc. What is it? It's 33.3. It's given. I know stuff here, just not all the numbers. Remember, the only thing that can go into a K equals is equilibrium stuff, the E row. So let's put in the E row. The PCl3 is X. The Cl2 is X. The PCl5 is 0.2 minus X. We okay? Let's keep simplifying. We need X. If we find X, it's game over. We win. Now, there's a couple different ways to look at the math here. I prefer cross multiplication. So it's the best way to teach it, in my opinion. So if you take that whole number and you put it over 1, since all whole numbers are over 1, you can then cross multiply to simplify. Here's a question I hope you don't miss. If I go this way, what is 1 times x times x? It's x squared. If you said 2x, your prereqs are not awesome for my class. 1 times x is x squared. So if you learn nothing else today, I hope you leave with that knowledge. What property of math will happen the other diagonal, though? Distribution. So first, it'll be this times 0.2. 33.3 times 0.2 is 6.66. Also very Halloween-y of me, I know. And then distribute 33.3 times negative x. Now, for those of y'all that know what quadratics are, you can see it. It's hiding there. But we're not ready to skip all the quadratic process yet. We don't have time to do whole quadratics in here. In order for the cheat that we're going to use in here to work, we have to make it a 0 equals expression. What that means is, I have to move everything to one side. If you move everything to one side of the equality, then there would be nothing. There would be 0 on the other side. But here's the trick. When you're deciding which side you're going to move over, I need you to know that you don't want the x squared to be negative. We want it to stay x squared, which means to get the 0, we need to bring this stuff over there. Now, it's simple algebra. Really, in a nutshell, all you're doing is flipping the signs. If you don't understand what that meant, to move this over, I need to subtract 6.66, and that's how it'll show up over there. I need to add 33.3x, and that's how it'll show up over there. Essentially, if you flip the signs, it'll move them over, which means this would be x squared plus 33.3x, and then flip it minus 6.66. And now we're very close. Now that'll take practice. If you're a little fuzzy, you're supposed to be. This is not a super easy class, as we know, but you're going to be fine. But let me show you the end here in 4 minutes.